Welcome to the lesson on properties of integers. By the end of this lesson, you will be able to state the closure property and verify the commutative property of integers under different operations. You will also be able to explain the associative property of integers under different operations and prove the distributive property of integers. Finally, you will be able to state the additive inverse and the additive and multiplicative identity of integers. Welcome to Treasure Island. This island is full of properties of integers under different operations. Only when you prove one property can you move to the next step towards the treasure.
Not to worry, I will guide you to the treasure.
Who do we have here? Are you another one trying to get the treasure? You will never ever be successful. Ha ha ha!
Psst! Over here. Don't listen to him. I will help you find the treasure. Once you find the treasure, all we tree folk will be set free. We have a spell over us, and that's why we are the way we are. I have the map to the treasure, but there is a riddle. We need to prove these properties on integers. As we prove each property, a small part of the map will unfold to reveal the way to the hidden treasure. I'm a math whiz, and we can crack this together. Come, let's find the treasure. What do we have here? The closure property of integers. That's easy. You remember that the sum of two whole numbers is a whole number. For example, the sum of 2 and 6 is 8. Now, let's add two integers, -2 and 6, and see what we get. We get 4, which is also an integer. That means for any two integers a and b, a plus b is also an integer. So we can say that integers are closed under addition. Look, I can see part of the map unfolding. Quick, let's move on to the next property. Now we have seen that integers are closed under addition. Can we also say that integers are closed under subtraction? Let's check this out with the help of an example. 2 minus 4 is equal to -2. -2 is an integer, and therefore we can say that integers are also closed under subtraction. I got it. If a and b are integers, then a minus b is also an integer. This is good fun. We have two more to go for this property. Multiplication is simple. We just multiply integers as whole numbers and place the sign before the result. Remember, the sign in the product depends upon the sign of the integers being multiplied. The product of 4 and -4 is -16. That's an integer too. So we have proved that integers are closed under multiplication. So it means for any two integers a and b, a into b is also an integer. We are now nearing the end of the first lap. Good going. Are integers not closed under division? Let's see if we can prove this. Now, if we divide an integer by another, the result should be an integer. -4 divided by -2 gives us 2. However, if we divide -2 by -4, we get -1 upon -2, which is not an integer. So we can say that integers are not closed under division. Great! We are done with the first lap of the closure property. Can't really see much. Time to move to the next lap. This is exciting. We're already on the next lap. Let's now tackle the commutative property under addition of integers. The commutative property says that we can add integers in any order. It is easy to remember the commutative property by thinking of integers commuting or changing the order of their places under addition. Thus, for any two integers a and b, a plus b is equal to b plus a. In case of whole numbers, the sum of 6 and 4 is equal to the sum of 4 and 6, which is 10. Let's check whether this is true of integers. When we add two integers, for example, -6 and 4, the result is -2. If we change the order and add 4 to -6, is the result still the same? Yes, it is. Look at these examples as well. So we can conclude that addition is commutative for integers. This is easier than I had imagined. We have seen earlier that addition is commutative for integers. Let's check if subtraction is commutative for integers. As you can see, 5 minus 8 is not equal to 8 minus 5. Therefore, subtraction is not commutative for integers. We have two more to go. I can see some interesting parts of this island now. We know that multiplication is commutative in case of whole numbers. Let's check whether this is true of integers. When we multiply two integers, -8 and 4, the product is -32. If we change the order and multiply 4 by -8, is the product still the same? Yes, it is. So we can conclude that multiplication is commutative for integers. Hence, for any two integers, a and b, a multiplied by b is equal to b multiplied by a. Hey, we're nearing the end of the second lap. Now, division is not commutative for whole numbers. Let's see if division is commutative for integers. Take a look. In these examples, we get integers equal to fractions as answers, which is not true. So we can conclude that integers are not commutative for division. We are fast approaching the end. I'm just waiting for you to get your hands on that treasure. Wow! We begin with the third lap now. I can only see the famous volcano of this island and Mount Fritz. Let's hurry. What do we have here? The associative property under addition. This property involves grouping of numbers. Take a look at this problem. Let's try and prove this with the help of the number line. First, we represent the sum on the number line. Now, we represent the second sum on the number line to check the final result. As you can see, the result in both the cases is the same, that is, -9. The example shows us that we can either add -3 and -2 together, and then add that sum to -4 to get the final answer. Or we can add -4 and -3 together first, and then add that sum to -2 to get the final answer. The answer will be the same no matter which way we do it. This shows that addition is associative for integers. Hence, for any integers a, b, and c, we have a plus b plus c is equal to a plus b plus c. Gosh, this is a bit tricky. I think we're getting closer to the treasure. Do you think subtraction is associative for integers? Let's check with the help of an example. Looks like it isn't. Thus, for any integers a, b and c, a minus b minus c is not equal to a minus b minus c. So, the associative property does not apply to subtraction. This was easy. We have seen that the associative property applies to addition. However, we need to check whether it applies to multiplication of integers. Let's try and prove this with the help of an example. In the first case, -3 and -2 have been grouped together. And in the second case, -4 and -3 have been grouped together. Let's check whether the grouping of integers in any way affects their final product. In both the cases, the product is -24. Therefore, the product is the same irrespective of the way the integers are grouped in the product. So, multiplication is associative for integers. Thus, for any integers a, b and c, we have a multiplied by b multiplied by c is equal to a multiplied by b multiplied by c. Okay, we have one more to go to complete the fourth lap. Let's check whether division is associative for integers with the help of an example. Looking at the result of this example, we can say that division is not associative for integers. We are more than halfway through the map. The treasure has to be very close now. This is the last lap, and I presume we will have some difficulties. Never mind, Integro never gives up.
You will never be able to get past this. I know for sure.
Now, the distributive property is applicable when a group involving addition of two integers is multiplied by another integer. So it involves two operations, addition and multiplication. It tells us that we can add first and then multiply, or multiply first and then add. We know that this property is true for whole numbers. Let's try and understand with the help of an example whether this property is true for integers as well. In this example, we can either add the numbers inside the brackets first, that is 4 and 3, and then multiply the result by -2. Or we can multiply -2 with each term in the bracket of the left-hand side of the equation separately, and then add the two products together. The result is the same in both cases. Similarly, look at this example. The result of both of these equations is the same. So, the product of -1 with the sum of 3 and 5 is equal to the sum of the product of -1, 3 and -1, 5. I just can't wait to get over with this property. The distributive property is also applicable when an expression involving subtraction of integers is then multiplied by an integer. Let's look at an example. So, irrespective of the fact that we subtract first and then multiply, or multiply first and then subtract, the result is the same. So, the product of 4 with the difference of 3 and 6 is equal to the difference of the product of 4, 3 and 4, 6. Therefore, we can say that the distributive property of multiplication over the operations of addition and subtraction is true in the case of integers. Yes, we have done it. Look, there's the treasure. Nobody can stop us from getting the treasure now.
I can. Didn't you read the fine print on the map? Ha ha ha!
Identities and inverses. That's the easiest part. I think the pirate has no clue about math. Now, let's crack the additive identity. We know that 0 is the additive identity for whole numbers. That is, the sum of any whole number and 0 is the same whole number. Let's check if 0 is an additive identity for integers too. Of course it is. So, 0 is an additive identity for integers. Thus, for any integer a plus 0 is equal to a is equal to 0 plus a. When we add 4 to minus 4, the result is 0. 4 is the additive inverse of minus 4. And minus 4 is the additive inverse of 4. Now, for the additive inverse. When 5 is multiplied by minus 1, the product is minus 5. Minus 5 is the additive inverse of 5. Similarly, when minus 7 is multiplied by minus 1, the result is 7. Therefore, the product of any integer and minus 1 is its additive inverse. Wasn't that simple? Just as 0 is the additive identity for integers, 1 is the multiplicative identity for integers. That is, when an integer is multiplied by 1, the product is the integer itself. Let's multiply an integer by minus 1. What is the result? As the product of integers, minus 1 and minus 5 is not minus 5, minus 1 is not the multiplicative identity. We've done it! The treasure is ours, and I'll be freed from my spell.
Congratulations! You have successfully completed this lesson. In this lesson, you learned to state the closure property under different operations in integers and to verify the commutative property under different operations. You also learned to explain the associative property of integers under different operations and to prove the distributive property of multiplication over addition and subtraction of integers. Finally, you learned to state the additive inverse and the additive and multiplicative identity of integers.